If you would recall, last time we talked about vector fields. So instead of our functions assigning scalars to all the points, our functions are now assigning vectors to all the points. This is a big leap. Like before this class, we had functions of one variable. We had scalar functions with one variable. To each real number, we assigned some other real number. And then all of a sudden at the beginning of this class, to each ordered pair, we're assigning a real number. Then each ordered triple, we're assigning a real number. So scalar functions went from functions of one variable to functions of two variables to functions of three variables, and we had to start imagining all that. And now in the same semester, I'm like, oh, instead of just putting a scalar as an output, we're going to put a vector as an output. And so everybody's like, oh, dude, we had just started functions of more than one variable, and now you're going to have the outputs be vectors. It seems a little early for that. And it is a little early for that, which makes it a perfect time. All right. So an example of a scalar function, temperature at every point in a room, it's just a number. An example of a vector field or a vector valued function is going to be the direction of airflow at every point in the room. So I can't describe which way the air is flowing with just one number. So I need a vector at each point pointing in the direction that the air is going. And then the magnitude will say how fast the air is going at that point. And the direction will say what, well, the direction of that air is going at that point. When we look at a graph of a vector field, we get a very different thing than we're used to. Rather than just drawing a one-dimensional curve for a function of a single variable or imagining a surface for a function of two variables, we get on the plane, we get vectors everywhere. Every point has a vector associated with it. So one of the examples we looked at was 2i plus yj. And on the x-axis, everything was these horizontal vectors because y was 0. Then as y increased, that increased the amount of vertical lift we got out of our vectors. But our horizontal direction was always 2. Keep one thing constant, change another thing to see how it changes. So we always had a 2, and then when y is 1, we had all these vectors. And then they would get steeper as we went up away from the x-axis. So down here is the x-axis. So as we get higher up, we see steeper vectors. And if we go a little further, these vectors are going to be steeper still. They're going to go 2 in the x and then 3 in the y. I didn't draw these last time. Now I'm figuring out why. Then when we look below the x-axis, the y values are all negative. So now my j component is going to be pointed the other direction. So it's going to go 2 in the x and then down 1 in the y. And then when we go further down, they get steeper but pointing down. So this was just our introduction to what's going on. At each point, we're assigning a vector. Rather than at each point, we assign a scalar. So the height, oops, I got to point it towards the camera. The height, it's very difficult to do. At each point, we're assigning a vector. Here are some things that we want to consider. Here are the things that we're going to consider as we think about these vector fields. First of all, as you're walking around today, I want you to notice vector fields everywhere you go. Just feel the air flowing around you. Maybe even feel how the temperature changes when you walk through a room, like there's a gust of cold air. You can notice that the individual temperatures at each point, those are scalars. Now imagine the wind blowing things around. Those are vectors. There's a little, some kind of event going on in the main room of this building, and they have food there. Notice the intensity of the smell and how it's changing as you walk towards there. And then remember that you skip breakfast, because young people always skip breakfast, and it's never a good idea. So first thing, get used to the idea of a vector field. Your vector fields are going to be in R3, unless you want to transport yourself, flatten out into the 2 dimensions to make things simpler. Might be kind of more complicated to do that than to just think in terms of R3. If it was 8y plus yj, then the vectors would just be longer this way, right? So right now these are 2i. So I go 2 in the x, and then whatever the y is in the j direction. So they would be this vector, instead of going 2 and up 1, 2i plus 1j, it would go 8y plus 1j. So it'd be a lot longer, but not as steep. This vector would not be at this 45-degree angle. Instead of going 2i plus 2j, it would go 2, 4, 6, 8i plus 2j. So it'd be a lot longer and not as steep. So here are the things that we're going to be interested in. So the length of the arrow is not quite. In this case, the length of the arrow, in this case, the length of the arrow is given by the I. But if I change the I, that's because I is just a constant, and we're just making a longer value of I. So notice that the length of this vector down here is 2, but the length of this vector up here is longer. The length of this vector here at -2, 2 is 2 times the square root of 2. So the magnitudes are changing because we have some y component going on. So the magnitude down here, the magnitude of this vector, not enough space. The magnitude of the vector at -2, 0 is 2. But up here, the magnitude of this vector field, the vector at -2, 2, this one's going up at a 45-degree angle. So it's 2 in the x and then 2 in the j is going to be 2 times the square root of 2. So it's a little bit longer. So length is determined by both components. Direction is determined by both components. But in the specific question that you asked, what if we change the 2i to an 8i but kept the yj? That's just going to change how the vectors look. They're going to be stretched out 4 times as long in the horizontal direction. Also, because they're stretched out in the horizontal direction, these are going at a slope of 1/2, right? Up 1, right 2. We could think in terms of slope. But the vector, if this was 8i, the slope would be 1 over 8, a rise of 1 over a run of 8. So it would be longer, but it wouldn't be as steep. It wouldn't be going at the same angle. So it would change a lot of things. The general shape of the vector field wouldn't be affected. But we'd see a big difference in the vectors themselves. Good question. It's all about taking one thing and then just changing something about it and see how that changes. Tinkering is a very important thing to do. It's like, well, what if I do this? So let's talk about the things that we want to know about vector fields. The things that we're going to think about, the two big things. Here are the things that we want to think about in a vector field. Number one, what is the flow of the vector field? What kind of curves is the vector field establishing? What is the flow of the vector field? That is, what kind of curves does the vector field establish? What kind of curves does a vector field establish? What does a leaf do in this vector field? If we just follow the vector field, if we just flow with the vector field, what path will we take? Let's take the leaf out of it. Let's put ourselves into the problem. If we just go with the vector field, where will the vector field take us? What path will we follow if we just follow the vector field? So if we just imagine starting somewhere, anywhere on this vector field, start any point x, y on this vector field, and just let the vector field take us along. So if I start up here on this vector field, we're kind of, we know that our horizontal is always going to be 2, but our vertical is going to increase as the y increases. So it's our vector is going to get steeper as we go up. And if we start here, we're going to be going up. So we're going to be, we can imagine we're starting off kind of steep. And as y goes up, we're going to get steeper. If we start lower, then we're going to be a little bit flatter, but still going up. And as we go up, things are going to get steeper. If we start down here, then we're going to be going kind of flat, but still going up. So as we go up, our path will get steeper. What kind of functions does it look like we're drawing over here? What kind of flow does this vector field have? I know we drew these lines last time. We want to think about it a little more. What kind of flow? It looks like we're building an exponential function because we just keep getting steeper, right? It looks like the flow of P is exponential. I forgot to call it a vector field. So in our example, that sentence came out really, really terrible. I made a wee bit of a bad choice here. Kind of pisses me off. Flow of this vector P of xy, all right, that reduces it a little bit. Looks exponential. Maybe I should just grow up, I don't know. I'll edit that out. I'm just kidding, I won't edit that out. It looks exponential just kind of from this hand wavy standpoint, because as we get further away from the x-axis, our vectors are going to get steeper, carrying us further away from the x-axis, causing our vectors to get steeper still. So yeah, that makes sense. Here's another way we could think about it. One of the things that we mentioned last time was, does this mechanically make sense? Does looking at this vector field, does it make sense that we should see this exponential flow? So can we make this intuition match the mechanics? Can we get the mechanics to match our intuition? We just kind of like looked at that and said exponential. We get this exponential. This has an exponential vibe to it. Can we make the intuition match the mechanics? Here's what we want to think about. Each of those vectors is the direction of some curve. Each of the vectors in this vector field is a tangent vector to some curve. So that's what we're thinking about with these vector fields. Each of these vectors, when we're thinking about flow, each of the vectors is tangent to some curve. Each of the vectors is going to be tangent to some flow line. So what the vector field is telling us is how x is changing in the with the I component, and how y is changing with the j component. So we're imagining this P of xy two I plus yj is a tangent to some curve. On this curve, we can see how the x component is changing. We see what the x component is doing. It's doing 2. This 2 is how x is changing. I'm going to imagine x changing with some parameter on this curve, because we've got this new parameterized curves technology. I'm going to say that's 2. That 2 is the dx dt. the I component is telling us how X is changing. The J component is telling us how Y is changing. Now we get to the other reason I did this problem in R2. I have how Y is changing with respect to T and how X is changing with respect to T. So I can figure out how Y is changing with respect to X. If you're watching me do this with our differentials and think this looks kind of fishy, don't worry, we're going to wave our hands at it. Notice if I look at dy dx, if I take dy dt and divide by dx dt, the dt's cancel out and I have dy dx. I can remove this parameter and see what dy dx looks like. Dy dx will look like dy dt over dx dt. Dy dt is y. Dx dt is a constant 2. What a vector field looks like is a system of differential equations. Now, we're not going to talk about solving systems of differential equations unless we can do some really, really simple stuff here. But notice what the differential equation for a flow line will look like. Dy dt dx is equal to y over 2. This is the differential equation. Y prime equals 1/2 y. We like this differential equation because we know this differential equation. We have solved this differential equation. We're saying that the rate of change of a function is proportional to the value of the function. And that tells us that the function is, like our intuition told us, exponential. So looking at that flow and imagining us just following the flow of that vector field and making an exponential function, we can resolve that with the mechanics. If we think about parameterized curves, think about the vector field being a little system of differential equations where dx dt is equal to 2 and dy dt is equal to y. Because of the way I constructed this particular vector field, it led to this nice, easily solvable differential equation. Because of course it was going to. That's what it was built to do. Any questions? This might seem like a lot, but that's only because this is a lot. Don't forget how far we've gone in just 11 weeks. Don't forget that 11 weeks is really only 10.5 weeks. Don't forget that of people that know this information and have this skill set, by knowing this information, by having taken this class, you are pushing up into generously top 10% of mathematical knowledge in the world. All right. So let's see if this, if we can make our intuition match on one of our other examples. If you recall, we also looked at 2i plus xj. Our intuition suggested that the flow line was parabolas. I get uncomfortable when I write lines are parabolas. Our intuition suggested that the flow was parabolic. We didn't confirm this. This was just the general feeling. We had negative slopes when x is negative. We had zero slope when x was 0. We had positive slope after. Further we were from the y-axis, the more negative our slope got, or the more positive our slope got. Let's do the same kind of thinking that we did in the previous problem. The I component is telling us how x is changing. So dx dt is still just a 2. That's how x is changing. And our dy dt is x. Very different look. So if I try to write dy dx by just dividing these, dy dt over dx dt, taking dy dt as x and dx dt as 2, this also leads to a nice simple differential equation, even simpler than the previous one. Where y prime dy dx is just 1/2 x. That means the solution y will be x squared plus some constant, just like our intuition suggested. We made the mechanics match our intuition. More importantly, we did the only thing that we ever do when we're learning math or trying to do science. We guess at what might happen, and then we just check. Find a way to check that that's what's the case. Yes, check. Yes, check. Tell people about it. See if they get the same results. Then we form consensus. And the whole time we say, this is how we believe this works, instead of saying, this is how it works. Or at the very least, when we say, this is how we believe it works, or when we say, this is how it works, we mean, this is how we believe it works. This is how our evidence suggests it works. Any questions? Always watch out for people that don't want it to work a certain way or tell you not to investigate stuff. They're the ones that don't want their beliefs challenged. That's dangerous. Y'all are going to college. At the end of college, you should have more questions. Some of you will be driven into a master's degree program because you have more questions. Some of you will have even more questions than that and be driven from your bachelor's degree program into a PhD program. If that's what you feel that you need to do, then you need to do that. Any questions? Comment? Snyder Law? How's everybody okay? So one of the things that we care about, things in the list of things that we care about for vector fields, things that we want to think about in vector fields, what is the flow of the vector fields? Another thing that we're going to want to think about when we're in a vector field is what would it be like to take a different path through that vector field? Flow of the vector field is just what the vector field does. Another question that we might be interested in is, what is it like to take some other path through that vector field? Not class. So first, we want to just think about the vector field and what kind of flow it has. What kind of paths are we determining just by building this vector field? The other thing that we want to think about is when there's a vector field, what is it like taking some other path through the vector field? When are we going with the vector field? When is the vector field pushing us along the path? When is the vector field pushing against our path? These are the things that the vector field might be doing as we're walking around in this vector field. Maybe the vector field is pushing us along, a tailwind. Maybe the vector field is pushing against us, a headwind. And then, of course, the question, because it's math class, how much is that happening? How much tailwind? How much headwind? How much is that vector field? How much influence does that vector field have on our path? Vector field, is it resisting our path or is it negative 1 times resisting our path? Pushing along, or is it pushing against? So imagine, here's the one that we have drawn. If I'm just like walking along the x-axis in the negative direction, we've got a headwind of -2, pushing directly into us. If we walk along, if I'm 1 unit away here, I've got not only a headwind pushing against me, but I've also got a vector pushing me down. So if I was going to walk along this path, it's just pure headwind. But if I'm trying to walk along this path, where where y is equal to -1, if I want this to be my path, then not only do I have this headwind of 2 coming at me, I've also got a headwind. I've also got this push of -1 from y. So I'm not only going to have to push against this headwind to keep on that path, I'm also going to have to push up against the vectors pushing down to maintain the path. So not just following the flow, because the flow will just flow, if we let go, we'll just flow down with this exponential. If we're trying to follow a path through a vector field, what does it feel like? Now, if my path is going just right in the positive direction along the x-axis, the vector field is pushing me along. The vector field is pushing me along. If I'm a little bit up from that or down from that, let's say at -1, the vector field is pushing me along horizontally, but I'm going to have to push back up because the vector field is trying to push back down. So the vector field is like, oh, go that way, go that way, go that way. And it's like, no, I maintain this path. So I can't just be like, oh, I'm going to go this way where the vector field is helping me. I'm going to push back a little bit to maintain that path. I got to put those things in balance. So this is all about what's it like walking through this vector field? What is the vector field doing at every point along the path? And moreover, how much is the vector field affecting our path? So here we have a question of how much are these vectors interacting? Helping or hurting? How much are these vectors interacting? Now, what I need to tell you now is super important, and it will make all of vector calculus snap into place. But only if I tell you like right now, after I introduce this question of what's the vector field doing along this path. But if I tell you right now, vector calculus just snaps into place. It becomes crystal clear if I tell you about this, how much tailwind and headwind. But I have to tell you right now, I can't wait. If I wait over the weekend, all is lost. We're going to have to go through vector calculus the normal way. So let's solve all of vector calculus right now when I tell you about how much tailwind and the operation that we're going to perform for how much tailwind and headwind. And it is, oh, darn, look at the time. That's going to do it for today. That's going to do it for this week. I'll see you all on Monday. Everybody have a good weekend, and thanks for playing. I should do like an actual streamer. Put it in the chat what you think the operation is going to be.